buttons on your computer.
Okay.
The buttons on it.
Hello, Mr. Ryan, are you right? No? Oh, I take that as a yes, okay?
No.
Okay, so we have talked about this problem
Hey,
for
Dad.
like 5 lessons, 4 lessons,
I
right?
smell coffee.
Okay, yes, because I drink coffee. Okay, so we talk about that same problem for like 4 days, right? So we're given an array of integers and we want to find out the duplicate. The duplicate is that 50% of the numbers, right? There are 2 n numbers and there are n numbers which are duplicate and all other elements are unique. So there are n plus 1 unique elements, right? Everyone? Yes? Do you get it?
Yes.
For example, like
You get
1, 2, 3, 3. What's the number we're looking for?
3.
Yes, because there are 3 appears 50% of the time, and then we want to look for it. So obviously we have a few solutions, right? Hash set, hash map. The data structure we use to remember the number we see. This is trivial. We can solve this number so we can compare the neighbor numbers. We can use the math, right? We calculate the sum of all the numbers and subtract the sum of all the unique numbers and then divide it by n minus 1, okay? And then we talk about the random, right? Random. So because the number appears 50% of time, if we randomly pick a number, it's 50% chance. And the second time we pick the index and it's another 50%. Times it together, that's 25%, right? On average, it takes 4 times to get a number. Right? When we talk about the complexity, we always talk about the worst case. So in the worst case, we will never be lucky. So this solution will never gives us the answer. But on the best case, on the best case is that,
First try, baby.
Yeah, first try, yes, exactly. It's 01, right? On the average case, is 4 times is still 01 constant, okay? We also talk about the burger sort, right? So sorting, right? So basically the monkey sort juggling, and then if there are n elements, so they are all together n factorial permutations, right? So only one of them is sorted. So the time complexity, in the best case, is just the first try, first attempt gives you the sorted array. That's all one. In the worst case, it never gets sorted, especially when n gets large. It's unlucky to get it sorted, right? But on the best case, on the average case, it takes n factorial time. So the time complexity is O n factorial, okay? In the average case, but it's still very large. This O n factorial is still very large, okay? So today we're going to talk about solving this using the pigeonhole. Okay, so can somebody summarize what's pigeonhole in 1 sentence?
I don't know.
Pigeonhole is like when you have like there's at least
Not all pigeons go on the hole.
at least like if you get 4 there are 10 marbles and you get 3 and you want to put them into a 3 piles with at least one of them having 3 of them, then at least you have, and the amount of tries like if the worst possible case is like each 2 cards and then so 6 and then 7, so it has to be 7 or 7 max.
Yes.
Not all pigeons have to go in the hole.
I was in pigeonhole and I didn't say pigeon once.
Okay, so simple. 3 pigeonhole. And then we have 4 pigeons. So we can get
Pigeons don't go in
Yeah.
holes.
Suppose our pigeons
No.
does. Okay, so
Terrible example.
okay.
Unrealistic.
Okay, let's forget about pigeon. 3 boxes, and we want to put 4 apples in. Okay.
Why would you put apples in the box?
Not all apples go in the box.
Okay. So we can get is that at least. Okay, listen up. At least 1 box contains what? Contains 2 apples. Am I right? At least, right? This is simple. 4 apples going to 3 box. So we know is at least 1 box has 2 apples. Okay.
But
Yeah.
not all apples need to go in the box.
Okay, so how does that help to solve this problem? So, for example, like 50% of the numbers are duplicate. What's the furthest distance? What's the furthest distance that if we want to place these duplicate numbers into this into this array? For example, like there are 2 n holes, and we have n duplicate numbers. If we want to put that in such holes, what's the furthest distance we can keep the duplicate numbers apart? There are 2 n. We want to put the n numbers. What's the furthest distance if we can put these numbers apart?
2n.
What's 2 n? 2 n here.
Yeah.
We have two n boxes and we want to put duplicate numbers in that. What's the furthest distance we can keep the n numbers apart? If we have 6 boxes and we have 3 numbers, what's the furthest distance you can keep those numbers apart?
1. No.
Furthest?
2.
2. Why 2? You can put it here, right?
Yeah.
And another here, but another number you can either put it here or here, right? If you put it here, the distance is 2. If you put it here, the distance is 2, right? Yeah?
Huh?
Okay. That's the pigeonhole principle. If we have a...
It was in my math book.
Yeah.
1, 2.
If we have n numbers, if we have 2 n holes, and we want to put the n numbers in, so let's think about the furthest distance these numbers can be separated apart, which is 2, right? Yeah, which is 2. We want to find out the maximum of the separation, which is the minimum. Okay. For example, here, if we put it here, if we put it, come on, please.
Yay!
If we put this number here, what's the shortest distance between any 2 numbers, which is this bit? Okay, so max of the mean of the data distance.
Max of a midnight.
Yeah. So okay. So for example, if we put this number here, the shortest distance here is 1, right? Is 1. Actually is 1. Okay. But if we put it here, this is 2. So we want to maximize the minimize of the data d. Okay.
So that's 2.
Yeah. So 2. So what does that mean? It means that we just have to check any subarray of size 4, right? Because in that case we can find the duplicate number. So the duplicate number must be in one of the subarray which is size 4. Does it make sense? So for example, like if we have 2n, if we have 2n here, so the best case we can put a duplicate number, right? We can put a duplicate number to maximize the data d. The shortest data d is we put this number here, and we skip this. We put another d, another separate number, another duplicate number here. Okay. So every other hole we put a duplicate number. Because there are n numbers, we want to put it in the 2n.
Bang!
Right? Yeah. But there is one special case, which is when n is 2. Okay, when n is 2, so there are only 4 holes, and we want to put 2 numbers, so we can put 2 numbers. Okay. Yeah, this is a special case. We can put it here and here, but it's also in the size 4. So we just have to go through this array. Check the subarray of size 4. Okay, if there is a duplicate here, alright. So for example, we can check this number equals this, then we return that. This number equals that. Okay, so every time we check that, and then we keep moving towards to the end. And what happened if at the end? One special case is that 1, 2, 3, 3. Okay, for example, given this is 3 is the number we're looking for. Okay, we check. Is 1 equals 2? No, we keep moving. Is 1 equals 3? No, keep moving. Okay? And then
What does that
2.
have to do with pigeonholes?
2 is 2 equals 3. Okay, I'll explain. Is 2 equals 3? No. Okay, then we end. Since we don't find it, then we return this number, which is the special case.
You can just do that without the pigeonholes. You can just look at the numbers. You didn't mention with pigeonholes.
That's what I'm saying. Pigeonhole. There are 2n
Yeah, but
pigeons.
like, okay.
2n pigeonholes.
One thing is 2, one thing is 3. You didn't use the pigeonholes. So you could do it without the pigeonholes. When you said, oh, 1 isn't the same as 2, 1 isn't the same as 3, keep moving on. Yeah, we could just do that method.
Yeah, sure.
Without the pigeonholes. Why do you need the pigeonholes?
Because I explain the pigeonholes to say that the duplicate numbers, okay, the duplicate numbers are how they are distributed, okay?
Like, oh, if
How they are distributed. For example, like 50% of the numbers are duplicate. So that means that every 2 numbers, on average, every 2 numbers, there's 1 duplicate number. Okay, and on size 4 subarray, they are the duplicates, right? There are 2 duplicates. Yeah, simple. You can think of it that way, right?
You could do that without the pigeonhole.
Yeah, of course. These are the methods without the pigeonhole. We are just talking about this to solve this.
But you could do that method without the pigeonholes.
We compare numbers, but we have to figure out why we can compare the numbers. Because I was just saying the duplicate number must be in one of the array of size 4. Okay, because there are 50% of numbers are duplicates. So it means that subarray of size 2 numbers, and any 2 numbers, there's 1 duplicate number. And if we double it, it'll be the size for any 4 elements, there must be 2 duplicate number, right? Simple. So we can just check any subarray of size 4 and then to compare if there's a duplicate, okay? There are 2 n pigeonholes. I want to put n pigeons in. The furthest distance you can keep the pigeon apart is by skipping 1, right? The furthest distance. So based on that, then we can say, we can check a size 4. Simple. This is how we apply the Pigeonhole Principle to solve this problem. Because we want to find out the duplicate number, and there are 2 n pigeonholes. There are n pigeons. The furthest distance we can keep any two pigeons apart is by putting it here, skipping 1, putting it here, skipping 1, right? So the furthest distance is furthest. Okay, so furthest, the max mean delta d. Okay.
Isn't it the max is put 1, skip 2, and then put 1?
But yes, good question. That's a very good part. If you put 1, skip 2, then you have less space here. So some pigeons must be next to each other. Am I right?
That's not nice.
So for example, like this one, 6 pigeonhole. You want to put 3, okay? So yes, you can put it here, okay? But here, the shortest distance is 1, okay? We want to maximize this. So how do we maximize this? We put it here, we put it here. This is the best case.
What?
Maximize the shortest distance between any 2 pigeons. We want to put 3 pigeons. Tell me the number.
1 and 6.
1 and 6, okay? 1 and 6, and then another one, you need to put 3.
4. 3 and 4.
4 then.
4, yes. Why you pick 4?
Because they're 2-way.
What are we doing here? So look, we can put it 4. Then the shortest distance is these 2, right? Right, this is bigger here, these 2 here.
Yeah.
Yeah, okay. But if we put it here, it's also okay, right? The shortest distance here. We put it here, the shortest distance is here. This is
There's
1.
no distance.
Yeah,
Why
okay,
do you
okay.
want the shortest distance? You said you want to maximize it.
Yeah, I want to maximize this shortest distance.
But if you maximize
That
the
means you
shortest...
need to shorten the shortest distance.
Yeah, but if you maximize the shortest distance, then it isn't the shortest distance.
There are 2 steps. First of all, get the shortest distance of any 2 pigeons, which is, and I want to maximize this value. Because once we have this max value, then I can check the window. I can maximize the window to check. What's the shortest distance between any 2 pigeons? You can put it here, right? Yeah? Put it here, shortest distance is 1. Put it here, 2. Put it here, this is 2. Put it here, this is 1.
4.
Okay? Make sense? And we want to maximize this, D. How do we maximize this, D? We put it here or here, because any here is 2.
Why do you want shortest when you want to maximize it?
If I get the maximize, I can have this window to check the duplicate numbers. Look, in this case, the duplicate number is 2, right? The maximize, I can put it 2. So I can say, okay, I want to size this. The duplicate number must be in this size 3, okay? If it's not there, I keep moving. Does it make sense now? I want to maximize this so I don't miss. So this argument does not miss the duplicate number. Right? Look, duplicate here. But if it's here, if it's this one,
You're saying maximizing the distance.
Look.
That's a window, not distance.
window of, in this case, is 2, right? It's actually size 3, right? If I put a pigeon here, this doesn't catch it. There's no duplicate, right? There's no duplicate, but it catches here. Now make sense now? Now make sense now?
A little bit, but you're saying that is maximizing the distance.
Yes, I maximize the
but
distance.
That's not the distance. That's a window.
The distance as the window, the delta D. I want to maximize the shortest, the mean of the delta D. mean delta D is the shortest distance between any two pigeons. And I want to maximize this and I choose this as a window to the maximize window. So I can rolling, sliding window, right? Sliding window thing. So I can find a duplicate because I know at some point the duplicate number must be in the size, in this window of size this. Okay, if this is size W, okay?
Yeah,
I
but
guess.
you're saying you're maximizing which is like the greatest and the shortest is like the least. And it doesn't make any sense because both of them are affecting the same thing, which is distance. Then why do you call both of them distance? If you say it like that, then it doesn't make any sense because if you maximize the shortest, then it wouldn't be the shortest anymore.
But these are not the same thing.
Yeah.
These
But
are
you
not the same
call
thing.
Both of them distance,
Okay, so let's call this.
which is why it doesn't make any sense.
Let's call it window, okay?
Yeah.
Maximize the value, okay? Maximize the value we get from the shortest distance. Does it make sense now? If it's misleading, okay? But you understand, okay? Okay, so now, yeah, I think we're clear. Then we can simply write the code. This is easy, right? So, define F array for I in range length array -2. If AI equal AI plus 1 or AI equal AI plus 2, right? So basically we're comparing if this number equal that or if this number equal that, right? Then if it is, then return AI. Otherwise, if we can't find it, then return the last number, return A minus 1. So where the special case is 1, 2, 3, 3. So simple. If 1 equals 2, return 1. If 1 equals 3, return 1. Otherwise, we keep moving, okay? 2 equals 3, return 2. 2 equals 3, return 2. Otherwise, we return last one. So another number, 2, 3, 3, 1, okay? So for example, like 2 equals 3, 2 equals 3, no. 3 equals 3, then we get it here. Okay, simple as that. Now, what's the time complexity for this one? Look at this. Yes, ON. In the worst case, this algorithm, for example, the duplicate, there are n numbers, right? There are 2 n numbers. So for example, like 1, 2, 3, 3, 4, here, n, here. And then all the duplicate numbers are placed in the second half of the array. Okay, in the second half of the array. And for this algorithm, it needs to go to half of it. Actually, the time complexity is ON divided by 2, which is ON. We drop the constant. What's the space complexity?
1.
1, yeah, because the
I
constant
said
space.
wrong.
Okay.
And I said the 1.
Okay,
I
so
got a key.
yeah, okay, so let's see you go today. Bye bye. Bye.